Today we're going to talk about graphing trig functions with multiple transformations. You're looking at the graph of y equals sine of x, that's the parent curve. But what if we wanted to graph something way more complex than that, like y equal 2 sine 2 x minus pi fourths plus 1? I'm going to show you three different methods for doing this. The first method is sort of an old school approach. Using your vast knowledge of transformations of functions, you know that each of these parameters affect every function in exactly 100% the same way. So you'll recognize that that is a vertical stretch by a factor of 2. That is a horizontal compression by a factor of 2 or 1/2, depending on the teacher that you talk to. That is a horizontal translation, pi fourths to the right. By the way, in trig land, that is sometimes called a phase shift. Sir, why is it called a phase shift? I'm not really sure why it's called a phase shift, actually. Why don't you look into that and don't get back to me on that. We also have a vertical translation, up 1. Okay, so now that we have the key transformations, we're going to take those transformations and transform each of the key points. So, by key points, I mean this point of inflection, max, point of inflection, min, and point of inflection. Okay, so let's start. This first point of inflection, we're going to vertically stretch it, horizontally compress it, move it right pi fourths and up 1, and that's going to take us to the point pi fourths 1. Okay, then we're going to take the max, and we're going to vertically stretch it, horizontally compress it, translate it right pi fourths, and up 1, and that takes us to pi halves 3. Now the next point of inflection, we're going to vertically stretch it, horizontally compress it, translate it right pi halves, and up 1, and that's going to take us to the point 3 pi fourths 1. Then I'm going to take this min, and I'm going to vertically stretch it, horizontally compress it, translate it right pi fourths, and up 1, that takes us to the point pi negative 1. And finally, we're going to take this last point of inflection at the end of our cycle, and we're going to vertically stretch it, horizontally compress it, horizontally translate it, and then shift it up 1, and that takes us to the point 5 pi fourths 1. And then you can repeat all those points because that's what periodic functions do, is they repeat. And once you have that, then you can graph your curve. Okay. It is important to note that primary trig functions have a lovely rotational symmetry about any point of inflection, which means you can go to any point of inflection, rotate it 180 degrees, it's going to look exactly the same. So you will never have a trig function that looks like this with the standard transformations. You're never going to have one that looks like this. You're never going to have one that looks like this. So when you are graphing this rotational symmetry can save you sometimes, because if you get a point there, a point there, a point there, a point there, and end up with a point over here, and you graph it, and you end up looking like this, you'll know you done messed up. It's possible you missed all 5 of those points, but more than likely, this is your culprit right here. Okay, now we're going to move on to method number 2. Okay, method number 2, we're going to start from scratch here again, and method number 2 is sort of a shortcut version of method number 1. What you're going to do is you are going to transform the first 2 points and then apply the symmetry. Okay, so we go through the same transformations we did in the last example. Okay, but now we only do it twice. So we start with that point of inflection, and the great thing about the point of inflection being located at the origin is it is affected neither by vertical stretches or horizontal stretches or compressions, nor by vertical or horizontal reflections. So the only thing that will affect that point of inflection is a translation. So immediately we can take that point right there and just go pi fourths right and up 1, and that becomes our first point. Okay, and now we're going to do the same thing with the max. The max is going to be affected by these other transformations though, so we are going to need to vertically stretch it, horizontally compress it, translate it right, and up 1, and that's going to take us to pi halves 3. Okay, so after you have transformed those first two key points, what you now have is this point of inflection. Okay, this point of inflection was transformed from a point of inflection. So once you make those transformations, there's no amount of transformations that can change the fact that that will be a point of inflection. That's important. Similarly with this max, once you've done the transformations on the max, there's no amount of transformations that are going to affect whether or not that's a max. Sir, what about vertical reflection? Ah, yes, you raise an excellent point. Vertical reflection would affect it. Vertical reflection would change that max into a min, but the process would basically still be the same. You would just go from your point of inflection to a min instead of a point of inflection to a max. Now what you're going to do is you're going to use this symmetry that we talked about. And now it really is a simple matter of counting boxes. To go from this point of inflection to this max, we went up 8 boxes and over 2. So to get to the next point of inflection from that max, we'll go down 8 boxes and over 2, and that puts me right there. Then we'll do the same thing again, down 8 boxes and over 2, that will put me there. And then over 2 and up 8 boxes, that will put me there. And now I have completed my cycle again, and I end up with something that looks like this. Okay, now very important to note this time that the wonderful symmetry that we used to save us last time is not going to save us this time because we used that symmetry in order to graph this function. So it's not going to catch any of our careless mistakes. For example, if we did our transformations in the wrong order, let's suppose we did this first point of inflection and we decided to do a vertical translation and then stretch it. So then what happens is we end up 1, stretch by 2, horizontally compress and right, and we end up with this point pi force 2 instead, and that is obviously a mistake. Now let's see if we do this max and end up doing it correctly, we would be at pi halves 3, and we end up there. And now what happens is, when I count my boxes and use the symmetry of this thing, I'm going to go 4 and 2, and then 4 and 2, and then continue to do 4 and 2, 4 and 2, until I end up with something that looks like this. Okay. Now, this red curve is the wrong curve. That's what can happen to you if you make a careless mistake in your first two. So be careful using this method. Now we're going to talk about method number 3. Method number 3 is probably my preferred approach. In retrospect, I probably should have started with that one, but I think it best demonstrates your understanding of trig functions. This is why I like this one. Okay, so this one starts exactly the same way as the other two. So you make that transformation on that very, very first point, that point of inflection. So we do exactly what we've been doing. So we just translate it pi force to the right and up 1. We end up at pi force 1. Now we use our understanding of trig functions. Okay, we know that the period is normally 2 pi for sine, and we know the only one of these parameters that affects that is this horizontal compression. So if I compress it by a factor of 2, the period of this trig function now becomes pi. And we know the amplitude is normally 1 for a trig function, and the only thing that will affect that is this vertical stretch right here. So the amplitude, which used to be 1, now will become 2. And now I'm going to use that information right there to finish my curve. If I know this is a point of inflection right here, and that's not changing from any amount of transformations, and I know that the period is pi, I know exactly pi later my cycle is going to end. So, starts at a point of inflection and finishes at a point of inflection. So we know that exactly pi more than pi force will get you to your next point of inflection. So all you got to do is add pi force plus pi, and that'll take you to 5 pi force 1. And if you're struggling to add fractions, really all you have to do is say, well, if I know my period is pi, and I know it is 8 boxes from 0 to pi, then all I got to do is go 8 boxes to get from this point of inflection to that point of inflection. Now I've basically got the beginning and end of my cycle. So I know if that's a point of inflection and that's a point of inflection, I know that right exactly in between those points of inflection comes another point of inflection. So I go right in between those 2 points and I get the point 3 pi fourths 1. Now, okay, now what must occur exactly in between 2 points of inflection? A max. And where are we going to go from there? Because the amplitude is now 2, all we have to do is go up 2 from that, and that's going to take us all the way up there to pi halves 3. And there's nothing going to change the fact that we have a max there. Sir, what about the vertical reflection? Yes. Vertical reflection, of course. If there had been a negative here, which there wasn't, if there had been a negative there, this would have not been a max, but instead been a min. So from that principal axis, you would go down 2 instead of up 2. Now we have one more point to do, and that's pretty easy. We go between these 2 points of inflection, and we know we're going to have a min. And how far do we go down? Well, we have to go down 1, 2, because the amplitude is 2. So we put that point in there like so, and then we have enough points. We'll go ahead and graph, and that'll be method number 3. I should probably also talk about cosine a little bit as well. So the big difference between cosine and sine, if I remove that and we'll graph cosine, the big difference here is the y-intercept now is not at the origin, but at the point 0, 1. So it will get affected by a vertical stretch. So what happens now is you vertically stretch it 2, it ends up there, horizontally compress it, translate it right pi fourths, and up 1 is going to take you to pi fourths 3. And now the big difference here is now we're starting at a max. So once you figure that period is pi, exactly pi later, you'll be at a max. And so this time, between 2 maxes, exactly in the middle, you'll find a min. So you'd have to use your amplitude, which is 2, and instead of going down 2, down to your principal axis, you'll go down 4 to get down to your minimum. And then go exactly vertically and horizontally in the middle of these 2 points and these 2 points, and that's how you would graph the cosine curve. Okay. Now the tangent curve is going to be slightly more complicated, so let's take a look at what the standard tangent curve looks like. Okay, that's the tangent curve. Now, if I wanted to graph something a little more complex than that, like 2 tan x minus pi fourths minus 1, the positive thing about the tangent curve is the point of inflection is also at the origin. So same as with the sine curve, all you really got to do is move it using the translations pi fourths to the right and down 1. So we end up with a point there. Now that's a point of inflection. Now the point of inflection occurs exactly in the middle of the 2 asymptotes, no matter what. So knowing that point of inflection and knowing that the period for tangent is pi and there are no horizontal stretches or compressions, so the period remains pi, there are 2 ways you could handle this. You could go exactly pi later from this point of inflection to create another point of inflection and then create an asymptote exactly in the middle of those. Or you could say, since the period is pi, I know that I have to go pi halves to the right of that point of inflection to create an asymptote, which is going to look like this. And then if I go pi halves to the left of that point, I'll create the other asymptote, which is going to look like that. And now that you have 2 asymptotes created, okay, now we have the last part. You could just wing it right now and draw it because you know a tangent curve is going to look something like that. And I'm going to go ahead and erase the original tangent curve. Okay, and so, but we want to be more specific. So what I'm going to look for is what we call the ones. Exactly between a point of inflection and an asymptote horizontally, we should have a point that is 1 up from that point of inflection vertically. But because we have a vertical stretch by a factor of 2, instead of 1s, they're now going to be 2s. So between this point of inflection and this asymptote, you're going to go right in the middle horizontally, and then you're going to go up 1, 2, and you're going to end up at the point pi halves 1. Similarly, the other way, you're going to go left and then go exactly in between that point and point of inflection and asymptote and go down 2, and you're going to end at the point 0, negative 3. And using those 3 points and that asymptote, you can now draw your tangent curve, and it's going to look something like that. Okay, that ought to do it.